Yes.
Okay. Let me share the screen.
Are we audible? Are we audible, sir?
Yes, you are audible. You are audible.
Just a general announcement. Online participant, please keep yourself muted until it is required for your side to ask a question. Yesterday somebody has unmuted and some voice in their coming. So I request you that everybody please keep yourself muted. And if you have a question, you are most welcome to please unmute and ask in between us. Aditya also like this, that in case whatever he is teaching, if you have any question, then feel free to start. Okay? But this is a gentle request for everybody that please be silent, be sincere in this lecture, because he is a very persistent teacher and he find very, because whatever effort he is putting, he also expects the same kind of effort from the other side. Okay, if you have been here, if he had been here, he would be teaching you by seeing your faces, and then he would not be able to do anything. Okay, but now since he is on the remote, so please be serious and show seriousness and ask questions, relevant questions. Aditya, stage is yours.
My screen is not yet shared. It is saying something. Now all of you can see my screen as well?
Yes.
Yes, it is visible.
Okay, visible. Okay, let us start. By the way, this topic we are going to cover is very recent topic, and whatever the generation that now we are seeing, everything, most of the things are actually being done using the diffusion models, and before that there were so many other types of models. But in the given amount of time, we'll try to see that what are some previous things, just a glimpse, and then we'll try to see that what is diffusion. From very top, there is good amount of mathematics involved in diffusion models, but we'll try to hide most of the things because of the fact that in the given amount of time, we can only give you the glimpse of what is going to happen. The diffusion models, they are the SOTA, and you can generate diverse different types of images as well as very high resolution images. And as you understand that even in the case of transformers, it was the thing that it is going to generate a large scale data and work on large scale data. Diffusion is also a model which can work on large scale data. That's the main thing over here as well, that it can be able to generate and work on large scale data. So many different types of architecture so far have came, like Glide, Dale, Imagen, and so on and so forth. But later, all of them are essentially being using one algorithm, and then that algorithm started to become better and better in the upcoming new, next generation generative algorithm, and that algorithm name was DDPM, that's a denoising diffusion probability. model. That was in 2020. And diffusion models are fundamentally different than other image generation techniques like VAE and GAN. But before that, you just see the amount of clarity and the type of images diffusion models can actually generate. They are mesmerizing, they are very high resolution, have every type of possible variation that you can have. Now there are 3 or 4 different time series which are being shown in the AI generative timeline. For 2014 VAE came, then soon after GANs and GRU actually came. Now GRU is like, auto-regressive, you can see that the auto-regressive and the transformer series, VAE variational auto-encoder series is in blue over here, and in orange you can see that the GAN generative series is shown over here. There are other series as well, and later you see that that is the series only after 20. So you can see that DDPM is here, and then DDIM, and later diffusion or the stable. After that, here probably you can see that the stable diffusion also came. So later diffusion, the stable diffusion, and this is the line onto which most amount of work started to happen. Those are essentially multi-model sort of generation, maybe from text to image or things like that. But this GAN series, you can see that this GAN series in orange, you can see that DC GAN, VAE, VQAE, and so forth. But GAN started to be much more denser because they were the state-of-the-art model before GAN, before the our diffusion model. So you can see that after this peaks to peaks and mu's and all different types of GAN, and finally they said that in 2022-23 style GAN, which was very good model and can generate so many different types of images, the things that you want to work on. So here you can see that the DALI and the glide and then image and party, muse, and so many. I mean, it's only up to 2023. In a year, 1.5 years, there are so many different types of new model games which are far better than what anyone can think of. And now one can say that diffusers are actually being used to generate videos as well. So if you wanted to see some image videos generated by diffusion models, Sora is a public platform of OpenAI. You go and check that you can see that very realistic short image clips generated by text, and by the way they are very good in generation. So the state of the art is really moving up, and recently I have heard a question that somebody was asking that how much time it's going to take from generating complete videos. I can say that's not very fast, maybe 2-3 years down the line probably it may happen, but yes, too much amount of handcrafting and human intervention will also be there. It's not going to be that you just write the script of a movie and directly the whole movie will be generated. Probably scenes will be generated and individual small time steps of a movie, they are going to be generated, and later you need to have human intervention to merge all of them and refine it into a complete movie also. So, but things are very moving in a very fast pace. Maybe in 3-4 years you are going to see such things happening. I'm not sure that whether GAN is covered in this or not, but I will take a very top level thing of GAN and VAE. But there are certain issues which were there in GAN, and diffusion is better equipped to somehow work onto that. In the case of diffusion timeline, that's also been shown over here that diffusion model early work started in 2015, and then you started to have so many different types of things coming each and every upcoming year. And amazing generation capabilities that in 2020 you can generate this, 2021 such things can be generated, and maybe in 2022 and 2022 text to video, such things were actually being generated. Very repetitive or simple videos were initially being generated. Now you can have very complex type of videos in a year or so, which can be generated from such amazing technology. This is a text to image prompt that I just wanted to show, in which you can see that the amount of amount of reality on each and every text which is being written, how it's been translated into the image. Like a female day trader with glasses in clean room. You see all that stuff being shown over here at her computer, looking out to the window. Now you see that the girl is looking out. She can be seen as a trade trader. Highly detailed, photorealistic, 8K, Unreal Engine. All these things are somehow being incorporated inside this image with so much amount of detailing in the images, and all these details are being one-to-one or most of the time being properly matched with the corresponding text. So that is the generation, which is the next level generation, and all these old things which were like GANs and VAEs, they started to be completely disrupted by this new technology. The other thing, again, you see that the type of detailing and the corresponding text was this. Again, it's very detailed, bookshelves and everything is being shown over here. So this is the image that's been taken from the paper, that is image generation from noise, and you can see that this whole network is actually being there. We'll talk about this. The good thing about diffusion models are that they are not very complicated to train. I mean, not very complicated to code. I have seen that the codes are most of the time not very complex so far as the code. But the theoretical part and the mathematical objective function is slightly complex, but although it boils down to only learning the amount of noise that was being introduced. So if I give you an image and if you can figure out that how much amount of noise this image is having, that is the whole purpose of diffusion. That's the whole purpose of diffusion. Okay. So it's a very long presentation, and I'll be not a presentation, it's just the notes. So basically I will try to show you certain things and will be hiding certain things. So just bear with the content which is being there and just try to understand what I'm trying to explain in front of you. This is GAN and this is VAE. A is GAN. So you can see that you sample something from a random space Z, show it to your generator. Generator is going to predict or generate an image for you, and once you have got this image, you show this image to the discriminator. By the way, this discriminator is having access to the real data. So these X's are coming from the real data, and X dashes are actually coming from the the generated data. And discriminator's duty is to differentiate between X dash and X. What does it mean? That discriminator need to just check it out that whether this generated image is coming from the real data or it's being generated by generator. So it's basically generator need to generate that sort of images which discriminator can assume that they are coming from the real thing, and at some point of time when discriminator completely got fooled, it will not be in a position to differentiate between the images coming from the real data or they are coming from the generator or the generator. Variation autoencoding is the other way in which generation can happen, in which you just take an image, show to that encoder, get a latent representation, and instead of getting that latent representation, variation autoencoders have been trained in such a way so as encoders are going to tell that what is the distribution from which these latent variables are coming from. And if you get that distribution, you sample a new data from that distribution, show it to your decoder, and generate a new image like this. And the loss function is that first loss function of such network is going to be that how close the X dash and X is, and the second, that's the reconstruction loss. And the other one is that how close the distribution predicted by the encoder is to the unit Gaussian. That's the KL divergence between the predicted distribution and the unit Gaussian. So these are the trading. Flow, trying to compute a flow models are trying given X, try to learn a function, and for decoders are essentially learning the inverse flow function for that X, and somehow they are also trying to do the things but not that much popular. And then comes the diffusion, which will say that I take an image and I iteratively diffuse certain amount of noise inside my network and keep on adding. At last, you are going to get something which is like Z, and that's a complete random noise. And now, from that noise, there's a forward process. Diffusion needs to learn a backward process by which you can iteratively remove, reduce, and iteratively somehow denoise the image so as you started to get the images or a way by which you can generate new images. The major difference between VAE and diffusion models are that in the case of VAE, the representation is containing the compressed information about the original image and basically tries to map the latent space into a runnable final decoder, which is going to make something from that latent vector to a real image. Diffusion models, or in the case of GAN, is slightly different, but in the case of diffusion model, it will try something else. It's not learning that how to compress the image and get the best possible this Z representation. Although diffusion models are close to VAE, but VAE tries to learn the distribution parameters. In the case of diffusion, we only learn that first we need to systematically destroy the structure, and iteratively once I destroy the structure by adding by adding small amount of noise at each step, I systematically destroy the entire structure. Then that will be called as the forward pass. And once the whole structure is being completely destroyed, you got a real noise. From that, backward process is going to somehow learn how can I reconstruct or denoise or regenerate the structure that's going to be in the real images. This essentially means that let's talk about one is generic question, that what's the difference between generation and the discrimination, the generative and versus the discriminative features. So let us understand that suppose that there is a child and you show that see this is A, this is also A, this is also A, and all different A's, you try to show that boy. Similarly, you show that boy are different types of B's. Some B is here and B and B. All of these are B's, all of these are A. So the type of problem for which a student or a boy, small kid is going to be trained is classification. And in order to differentiate between A and B, this guy needs to understand discriminative features. What does that mean? Discriminative features means that if it is in an A, there are 3 lines, but maybe in B, you have 1 line. Even if you can learn this, probably you can differentiate between A and B. Although they are not going to talk about all the geometry and the other important curves and information which is there in A and B, but instead you just try to learn certain key variations by which you can differentiate between both of these classes. Such features are only needed when you wanted to do classification. But once you train a student or a boy or a kid that this is A and this is B, and later you show, hey, tell me whether this is an A or a B, he can tell that okay, whether it's an A or a B. But do you think that as soon as that student or the small kid, after seeing limited amount of example, can differentiate between A and B, but can they generate here? You just say that write an A now. That guy may not be in a position to write an A. He may not be in a position to write a B, although he can differentiate between A and B. So what means that the generative features are different than discriminative features, because the generative task itself is very different, much more detailed and complex than classification, and that is why you need much more comprehensive set of features and learning so as to do the task of generation. So in the case of diffusion, so let us see it in a different way, that learning or generation as denoising, how can we do that? So our question is that how can we help or teach a small child to draw A or B? Now instead of saying a small kid that hey, this is A or B, can you differentiate between A or B? Let us say that can you draw A or B? What are the ways in which somebody can train or teach a child to draw A or B is the question. And it is certainly not the way in which VAE and GANs are working. VAE and GANs essentially tries to learn different, different distributions. One is trying to learn the distribution of the latent representation Z, and the other one is trying to somehow hold of the distribution of X or the images itself. But both of these things are not the way in which you actually want your kid or a small child to be trained to draw certain things. How we let our kids to understand or teach them how to draw an A is very simple. It is example number 1 in which you can see that we give them points, and usually these points are very close to each other, and then we will say, hey, join these dots. And when you started to join these dots, at last you will say, hey, this is an A. Later, when this guy, the small kid, understands to join very close white dots, later we can say that now the dots are getting slightly far, and then eventually they become very distant. Guidance points are getting distant to each other, and if somebody started to somehow draw lines like this, joining these points in a suitable manner, probably you have a way in which you can generate A. That's a generative feature. And at some point of time, you will understand that learning in this way, learning generations in this way, you can somehow also learn how to generate certain character A, B or C from completed noise. And that is the thing that you are looking for. There is no information available, you just need to learn that given a noise, how can I generate data for you? Example number 2. And that's the way in which essentially diffusion models are going to work. Let us take an example number 2 to understand that how can we generate something by denoising. Basically, iteratively doing denoising is the new paradigm of generation, which is essentially being utilized and being somehow being introduced by diffusion model. Let us say that this is the piano that you are trying to learn. This is the piano or a guitar that you wanted to learn. And you wanted to play Tujhe Dekha To Ye Jana Sana. This is the song. So you wanted to play this song. And you also know the ground truth of this. So some music is there, ding, 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 ding. Some music is also there. So you know that what's the music. And you know that okay, I wanted to play this. Initially, you play something. If I give you a piano and if you don't know, you will play something completely jerk. That's a completely jerk, the random noise. So some random noise is there, and what you are trying to do, you take that random noise, and basically you initially play as a random noise, and then you think about that what's the ground truth. Depending upon your ground truth, you try to adjust yourself, and then you will see that you started to adjust it in such a way so that you started to get yourself closer towards the ground truth. But it's not the case that in the next round, after listening to the ground truth, you can generate the whole song. It's only that you will get for Tujhe key you somehow got, but other things are completely random again. So you iteratively try to denoise the noise that you have generated in the first step, and slowly iterative denoising is going to take you closer and closer somehow towards the goal that you are looking for. So this can be actually seen as denoising and learning denoising so as to generate the data. So it's that you have got a complete noise. Given this set of complete noise, you try to remove the noise, some amount of noise from that, and if you can remove that, you get a slightly lesser noisy version. You again try to remove the noise from that, then you got something which is better than the previous version, and then again you denoise something, and you got the something which is slightly relatable to some sound also. So that's the iterative refinement which is somehow going to happen. So the same thing is going to happen when you are going to use diffusion model, and this can be with respect to the image as well. So if you have a ground truth, you try to somehow take it, denoise your data in such a way so that you started to go close to the ground truth slowly and slowly. So basically, we need to train a neural network that will take some noise and try to understand how can I denoise it with respect to a particular goal or the output, the ground that you are looking for. So forward pass is just to, we need to ensure that the noise is just added iteratively to us, as slowly as possible. So you have got a new good quality image. Onto that, you slowly at 100 steps or 500 steps, you keep on adding certain amount of noise, and that noise should have to be added iteratively and slowly, which essentially means that only small noise is being added. And in the backward process, you try to ensure that one can recover it back. How? By learning. What you are going to learn? You are going to learn a noise. So there is going to be a neural network which is going to take the noisy image from you and try to learn that how much amount of noise should have to be removed so as to get it one step closer towards the corresponding ground. But again, you just think about noise. So if I say that there is a ground truth, you have an end goal, but when you are generating, you have a noise, you don't have an end goal. So if we say that there is some noise and you wanted to denoise it and there is no end goal, then this problem itself is a ill-posed problem and it's not well defined and not a meaningful thing even. If I give you something and say that, hey, denoise it, then you will suggest what to denoise, what you want to make. For an example, suppose that you have raw vegetables and I say cut them. So you say, okay, that is a type of denoising, I am doing some processing onto that. But then your question will be that, hey, I will cut, but you tell me whether you wanted to make it Mughlai, or you wanted to make Chinese, or you wanted to make veg salad. So depending upon the type of dish that you want to make, the cutting has to be done. The type of image that you want to generate, denoising is going to, happen in that way. Otherwise, denoising without a particular ground or without a particular goal doesn't mean anything. So while training, we usually have ground goal. For example number 2, you can similarly, you have a raw stone. From that, some person is going to carve, certain sculptures out of that. And initially it's a raw stone, and with his small hammer, it's going to somehow chip it off slowly, and it's actually denoising that raw stone, and it's somehow trying to carve it. But then I said denoise it, but he will say that, hey, denoising for Hanumanji is different and denoising for Shankar Bhagwan is going to be different. So denoising is, we understood, that has to be dependent upon not only depending upon the end goal that what you are going to make. And end goal is only being there when you are going to train your network. So during training, we know that we have started from this image and we keep on adding noise. So while coming back from backward path, we at least at every step know that denoise it so that it becomes one step closer towards the ground truth. But it's not the case that denoising is only going to be dependent upon the backward pass, or the denoising is only going to be dependent upon the end goal. It is also going to be dependent upon the time step. which means that in the initial time step, suppose that coming from the noise, you have got an original completed noise, and now you do first denoising. The first denoising completely be a bigger denoising step. A bigger denoising step means that you can have a bigger Gaussian by which you can denoise your data. And when you become finally close to the image, suppose that now or almost image is being made, and now you got small amount of fine tuning and sharp image details that you wanted to add, then it is, the final step has to be closed. So as you understand that somebody is doing makeup, then initially his or her hands on your face are going to be very fast. And later, at last, only fine tuning is going to happen on the face, then you can see that the brushes strokes are going to be small. In the same way, an artist is drawing initially, once the whole canvas is, white, he or she is going to have longer or bigger denoising steps, basically adding too much amount of stuff. At last, when the whole thing is being done, very small amount of or very small denoising steps are going to be taken. So it's not only denoising is being dependent upon what you wanted to make, it's also going to request that please tell me what you want to make, as well as tell me that at what time step right now you are. Depending upon the time step, I will choose that which brush I need to choose for doing the denoising. So now you can see that okay, this is x0, this is x1, x2, x3, x4 and xt. So this is the original image. This is the original image, and given some maths will be there in the given amount of time. I may not be able to cover, but I just show you the glimpse of that. Some noise, the image is there, and the x0 basically this is the image, and given this x0 as the image, I add small amount of noise and keep on adding small amount of noise, and then it will become this and this and this, and at some point of time you will see that it becomes a completely random noise. And at each step I am just ensuring that I am adding a small amount of Gaussian noise inside my data. So you just see, you can just see that forward process is nothing but here it has to be xt is equal to xt minus 1. This is written wrongly, it is not xt, this is x of t minus 1, and that's the noise that I have got. And if I say that you have got some noise, and if you wanted to somehow multiply that noise with under root of beta and alpha, and all those things are certain hyperparameters of my denoising step. But you can see that it is nothing but the reparameterization technique in which I am going to say that beta is a number which is close to 1. So our noise is here, which we are going to add. we have collected some noise like this, and this is the t minus 1th time step, and I just take a t minus 1th time step, scale it suitably, and I take a noise, and I also scale that noise suitably, and then add both of them so as to get the tth step data. I explain it again that at every step I am adding noise. This is x of t minus 1. I take the previous step data and suitably scale it, and then I take a random number generator, Gaussian random number generator, and ask it give me a random noise. I take that noise and randomly and that suitably scale that noise as well, and I add. Once I add both of them, you are going to get another next step. Next step xt, that is going to be the way in which from xt minus 1, how can you go to xt? So if I give you x3 and if I give you a random noise, you take that random noise, multiply by this, and then take the xt data and multiply by this and add both of them, you are going to get x4. So from any xt minus 1, how can you go to x, x of t? That's the somehow a way by which you just add it. So forward process, these betas are fixed, beta t is fixed. So beta is, starting from a small 10 to the power minus 2 and keep on adding depending upon the time. So beta 0 will be 10 to the power minus 2, beta 1 may be 10 to the power minus 2 plus something and so on and so forth, and will linearly increase beta, which is essentially going to say that the amount of noise that you wanted to add to your previous time step, how that noise is being scaled, and that is the amount of noise that you are somehow trying to ensure and that you are trying to introduce in your previous previous time step. If you keep on doing for say first step, second step, third, fourth, fifth, and so on and so forth, at some point of time your data started to be losing the structure, and slowly, gradually you will see that it's got completely into the noise. You can see here that that's an image A, that's the image B. You keep on adding, there's some amount of noise, that keep on adding this noise systematically. Why is that systematically? Because beta is fixed, so we know that what is the amount of noise that I am adding. Why I am systematically adding? Because if I add systematically, I can learn how to remove this noise. So you take this as your data, train a network in such a way so that given an image like this, if somebody can tell me that how much amount of noise was being added onto this, and so that I can get from B to A, so I know that how can I remove the noise. So if you can remove the noise iteratively, step by step, then probably you can start from this completely random image. And if it has taken 1000 time steps, which means that 1000 times I have added noise to the data like this, and then I got this, then iteratively I can go back and back and back and back and back, and finally I will reach to some new generated images like this. So here you can also see that this is a completely noised version, and then because in the backward, so this was actually being called as the forward process, in which you just add noise. There is no learning involved in the case of forward process. The simple reason for no learning involved in forward process is that I will start with x0, which is with me, and then I sample some noise that I can always sample beta t and under root of 1 minus beta t. All these things are hyperparameters which are dependent only upon t and already being fixed for us. So we need not to learn anything in the case of forward diffusion, and we can start from x0 and can reach to xt in some t steps by keep on adding Gaussian noise into your data. While the noise, then you need to learn, that's the learning that you have to do that from C. How can I come from D? That's a very big time step. It's not going to be just a pictorial. I have shown that from this, how can I know that how much amount of D noise one can do, so that if this is xt or x1000, from that how much amount of noise should I can remove so that I somehow get x 9,999, and keep on doing so as to get the denoised version, and at some point of time probably you may reach there, but mostly this is a stochastic process and noise is being reduced, and your network is going to predict this noise, and it's a stochastic process, because of which you can see that instead of reaching up to there, probably you may reach to the other allied versions of the small variations which may happen due to the noise. So instead of maybe reaching to the exact one image, you may reach non-deterministically because of the stochasticity to several different types of images. That depends upon what is the iterative denoising that you have done in each step. The forward diffusion is that xt to xt minus x, xt minus 1 to xt. That's the forward process. The backward process is that how can I go from xt to x0. So by the way, if somehow you can learn that how can I go from xt to x0, that is generation. So that is why I have said that generation via denoising. This is a new paradigm. So if somebody can learn that how can I go from x t to x0, it's just a new generation, that a completely noisy image is being given to me, and I can somehow convert that completely noisy image iteratively into a x0 no noise image, which is essentially a generation. This can actually be seen as generation, the new paradigm. And for this, what you need to learn iteratively in small steps. Even if you can learn in small steps that that x of given, if I give you x of t, how can you make x of t minus 1 out of that? So from, if you can even learn how can I convert something from xt or x 500, how can I make x 499? If I give you x 456, how can you make x 455? If I give you a method by which you can do that, basically if you can learn this, then basically that's the forward thing. But if you can learn this, the reverse thing, basically that's the generation. Forward is nothing, no learning is there. Forward is just an addition of a predefined fixed Gaussian noise into the data. If you can somehow learn how can I come back, basically you have got a hold on denoising, and if you can iteratively denoise it for a good amount of time, you probably reach to the denoised version of the data. So certain things are there, and probably for most of them we have the corresponding equations and all, but we will not be going into the details at why they have chosen under root beta and 1 minus beta times under root of 1 minus beta t and all. We are not going to use all that stuff because it's slightly time consuming, but too much amount of math, even in the case of forward pass, is there. But it's a detailed thing. But essentially, what you need to see is that from x, that the you can see that the image is there, and you can see that that is the linear beta, that is the cosine beta. So linear beta means that beta t is gradually decreasing in the form of a linear function, and you can see that a dog is there and its structure is linearly getting reduced, and at this point of time got completely removed. This is the cosine structure, cosine schedule several times, because the noise is being added as a particular schedule which is being governed by the beta thing. And you see that here the structure is there for a longer time, and in certain papers they have shown that most of the time cosine schedules are slightly better than the linear schedule. So here you can see, and probably I will try to somehow give you that this is x0. So just see that this is xt minus 1, and from here xt, when we are going via this arrow, this is nothing but addition of 12. Diffusion or the reverse is basically denoising, and which is being parameterized. Q is not parameterized. Q is a defined function of just adding the noise. Reversal is a function that we need to learn that can take xt and convert it into its corresponding xt plus xt minus 1, and we don't know that, so that's why we need to learn that, and we are going to learn this via parameter theta, via the set of parameter theta. And it's been shown that xt is going to be converted into xt minus 1. I wanted to learn this theta. Theta can be the parameter distribution parameters that the distribution we are trying to learn for this probability density function, which is essentially somehow going to be, and it's a Gaussian assumption is being made, and because we have added the noise as Gaussian assumption, that every noise that we have added at any point step, any point or any time step is nothing but the Gaussian noise. So we keep on adding Gaussian noise, and we are assuming that by coming back we need to learn the Gaussian noise. So if it's a Gaussian, then it is going to have two things, this as well as this. So there's that is the mu of that Gaussianness, and that's the sigma of the Gaussianness. So basically we are trying to learn the distribution which can, from which we can sample xt can be converted into x of t minus 1. So that's the theta parameter we are trying to learn of a distribution of this, and this probability distribution is nothing but going to be a Gaussian from our assumption, and this Gaussian is going to have two set of parameters, mu as well as the sigma, and both of them are also being parameterized and going to be coming from this theta network. Mu and sigma are going to be dependent upon what is xt as well as the time step. What is xt, the corresponding input, and the time step. So if I only give you xt like this, and if I give you t, the time step, can you come back to this? So it's again, as I have said, it's going to be a ill-posed problem, because given only xt and a time step t, you just don't know that what you essentially want to make. So during training, you have x0 and you have taken this step, and while coming back, you can tell your network xt is this, t is this, and along with that I wanted to make x0. Can you tell me that what's going to be the suitable noise, or basically what was the noise that was being introduced? And can you denoise this xt in such a way so that it becomes one step closer to whom you have to tell? That's why you have to tell x0. That's why it's a doubly conditioned problem, in which first you need to condition it on t, and then you need to condition it on x0. So again, for the reverse diffusion cases, there are going to be many constraints and all, and certain. So as I have said, that from A to B, if you are going, if it's A to B and you are adding a Gaussian, then from B to A you can come by removing that Gaussian. And other assumptions are also going to be there, because this is going to be a huge, mathematical jugglery. So that they have conditioned all this probability distribution learning in such a way so that it becomes doubly conditioned, because individually without the thing onto which you want to come back, x0, if you don't tell me while training, even I don't know what's going to be the ground truth, and if you don't know that what's the ground truth, then how can you train a network? So it's been shown that you wanted to learn this distribution, that is from xt, how can I come back to xt minus 1? And the assumption is that it's going to be parameterized by theta, and this theta is going to be coming out by a neural network. So what's going to be the input? So input to this neural network, theta, the inputs are going to be, I may have written somewhere that the inputs to such thing is going to be, so the p theta inputs are going to be xt and t, and you may get this output, but as I have said that xt and t alone, it's a ill-posed problem, so you need xt, t as well as x0. So it is going to be that xt, t and x0, three things will go inside. So as I have shown that x0, so it's going to say that xt to xt minus 1, we can't do that, it's an intractable thing. So let us do it that you wanted to make xt minus 1 fine from xt, okay, but also give me x0 as well as the current time step, which is being t. So these three, xt, x0 and t, these three things are going to be the input, and using all these things you need to somehow generate and give me that how can I make an xt which will make, xt minus 1, which will take this xt one step closer to whom x0 things which are in my data set. Right, so some again, math is being done, and later it's been shown mathematically that you just have to, in summarization, in summary, what we need to somehow suggest, or what we need to say is that that essentially this, the loss function completely is that tell me that what was the noise. So I somehow go and introduce some noise in my xt minus 1. I take xt minus 1, add some noise into that and make xt, and later I said my network that see, this is xt, predict that what was the noise that I have introduced. Understand it again, the whole thing, because again this will also take some other understanding which I have not covered. So from top, I am just trying to summarize that what's been happening inside this, that you take an x of t minus 1, say x 55. You take, introduce a noise, it will become x 56. Now you take that x 56, show it to your neural network and say, hey neural network, I am showing you x 56. Can you tell me what's the amount of noise that I have introduced so that it can become x55? Along with that, you also say that actually I wanted to make x0. So from basically unconditional denoising, you have converted into a denoising step which says that x56 need to be denoised one step closer towards x0, and all these things are being fed into the network. And just what's the difference? You know what is the noise. That's, this was the noise that I have somehow been sampled. This is the noise by which I have made the data, and this is the noise which has been predicted by my network. And that is essentially, this is the mathematical formulation of x of t. So I take this xt, show it to my network. Epsilon is a network. Epsilon theta is a network which is going to tell me the parameter theta of my noise. So this network is essentially telling me, this is a single network. This network is telling me that if I show you xt, which is as I have said, so this is xt, I show it to my neural network and say, hey, can you tell me that how much amount of noise I have added to make you, and as I have sampled myself this noise from my data. So my network is being just differentiating, or one can say that figuring out the distance between the noise that I have sampled by which I have generated the data, as well as the data generated I have shown to my neural network and say that tell me the amount of noise that I have used to generate that data, and effectively the difference between both of these noise is going to be the recent step. It's the simplistic version, and for this unit is essentially being taken. So input is, suppose that if your input is of size say 256 to 572 by 572, then your output is also here is the segmentation map. But if it's the same unit type of network is going to be taken for diffusion modeling, then the image size 572 by 772 will be the going inside the unit, and the same amount of size as 572 by 572. So per pixel noise you are adding, and you have got here as an output. You are not going to get a segmentation map, but essentially the error. So xt will go in, and network has to predict that. After doing all that stuff, can you please tell me that what was the noise? So that is the noise, and you also have a noise sampled onto which you have applied on xt minus 1 so as to make it xt. The xt goes in, so first you sample a noise, make xt from xt minus 1, take that xt, send in your network, get the corresponding error, or get the corresponding noise, and take that noise and find out how far this noise is from the actual noise that I have sampled, and then subtract both of them and figure out that how close they were, and depending upon that you train your loss. So that the unit is again being used. This unit is only doing what? This unit is taking a noise and predicting out how much amount of noise it is. How can I denoise this to get one step closer towards the corresponding output. Once it's been trained, essentially this network is trained generically. So it will take any noise. Suppose that our assumption is that capital D is equal to 1000, which means that after 1000 times adding noise, small Gaussian noise, if I add 1000 times to a real image, it will become a complete noise. Now, suppose you take and train this network in the way I have said. This noise, this network can know what's the amount of noise, and basically you can use this network to remove the noise. So you take a completely random image and remove 1000 times noise from that using this network. You take 1000 x 1000 show it will give you a noise, remove that, it will become x999, you show it again remove, again show, again remove, and keep on doing. At last, after 1000 times steps, after refining the data, you will get an image which is very close to a real image. May not be the image by you are looking for. It's not right now a controlled version. Then for controlling, that you want to make something specifically, then you need to have other few more constraints, and then it becomes constrained diffusion modeling, like controlled and other networks are also being there. But in this case, it's just like a GAN. GAN is taking some random data and generating images. VA is taking some random data from unit normal distribution, generating images. Similarly, diffusion model takes this fully trained network for the noise generation. It will take a completely noisy image, go inside, get a noise, and remove that noise, and then keep on feeding it and iteratively generating better versions having lesser noise. And after capital T type of check out, it is typically 1000 or 10,000 times step, depending upon that what is your capital T, you will get a denoised version or a new image generated by that noisy data. The same thing is being shown over here. By the way, this is happening in the latent space. So there also guys have said that, see, instead of working directly onto the image, you take this X, show it to an encoder, and got a latent space in that. But instead of denoising X, it's the status denoise in the space of Z. So I have talked about that diffusion in image space, but instead of adding noise in images, you can add noise in the Z space. That is essentially going to be the latent diffusion. So you can say that X, then you have got the encoder, you have got an encoding. Over this encoding, you add noise, you have got a completely noise vector, and then you show it to the denoising network, and this denoising network is happening applied how many T-1 capital T times basically, because one time here and T-1 times over there, and keep on repeating, and finally you will get the Z, and then you show it to the decoder, and then you will get the finally generated image. So the diffusion happening in the latent space, that's what is latent diffusion. Diffusion happening in image space, we just have seen. So there are far better style conversions can be done. Text to realistic images can be done. Certain limitations were being there at least 1.5 years back when I was writing this text, and that was that faces can be distorted. I mean, it can generate good faces and all, but if you can generate faces, I mean, if you wanted to generate images like this, at that point of time, it was not in a position to make very good quality faces, as well as the eyes and other things, counting number of faces. I mean, if you want 5 faces, several times we started to have good amount of errors into that. So diffusion models are currently bad in generating from the text to an image, but fairly it can generate other details, but facial, everything, along with all the things of the scene itself, it's slightly complex. But as I have said, that things are very fast and grown up, and maybe in a year, most of these challenges may have been removed. At least CVPR, ICCV, ECCV, and all 3 or 4 conferences happened in this year. I am sure that in 2024 all these things are going to be removed, and we are getting very good performance. This of my presentation is anyways publicly available on my LinkedIn site. If you wanted, you can go and see my LinkedIn profile. From there, you can get this presentation, as well as if you wanted to read about diffusion model in details, or at least the places from where I have covered these things, and because basically I have learned things from the places. The link back GitHub repository is there. I mean, there's an excellent blog post is there. which talks about all the math. I have read all the math from there. So you can read things from here, and then two other resources from which they have talked about diffusion models is being shown over here. One or two places, JLMRs, this last one, if you are really new and not much aware of diffusion, and if you want a very high level description, then JLMR, top level non-technical description is also being there, but a detailed tutorial, which is an excellent tutorial by Calvin Leo, but this needs huge amount of prerequisite and all possible math related to diffusion models is actually being covered in this detailed tutorial. So I am done. Thank you very much.
Thank you, Aditya. Thank you for the enlightening session.
Sir, I have a question.
So, any question from the audience?
Sir.
Yes, please go ahead.
Sir,
One minute. Thank you, Aditya. Thank you for the excellent session. I think I was not audible. I have spoken those things. Just repeat once again. So, all right. The questions from the audience. I think we can take few questions. The first question is from the offline audience. Yeah, go ahead.
Okay, sir. A very good afternoon. I am Udit. Sir, while the technical and mathematical part will take a few visits, but I have a question in the theory that you talked about diffusion models and how the forward propagation here will convert a proper image into slowly into a noised image, and then the back propagation and like maybe discriminator or the second part of the model will now convert this noise back, will try to reconstruct the image using this noise. Is this right?
Yes.
Yeah, so sir, I have a follow-up question here that now what is the limit up to which an image can be keep on adding noise to that image? I mean, there must be a certain limit to it, right? That an image of a dog or an image of a horse will not be differentiable after a certain point if we have added too much noise, right?
Yes, good question. Let me answer it. So the point is that there is no limit, and the point that you need to understand is that if it's a completely random thing, you just need to make one small step, very small close step back to a slightly better image. So let me show you, maybe if I have, just see that if it's a completely noise version, you anyways not able to get the whole thing back. Now just see that from this, if this is the thing, you can't make this thing in one step or this thing in one step, and it's not desirable as well. I will show you this and you can make this. I can show you this and you can make this. If I show you this, you need to learn how can I make this. If I show you this, you need not to learn it from this. How can I make this? From this, you need to learn how can I make this. Is that okay? Is that your question?
No, sir. I was talking about that the first part of the model will keep on adding the noise, right? It will not stop at the third image in this.
Yeah, that's what I'm telling.
So we will train the diffusion second part as well.
It has to be a completely noise. I mean, you take the image, keep on adding iteratively noise to it until and unless the whole image is being converted into a noise. Is that okay? First of all, first of all, this is okay. Then I come on to your question.
Yes, sir. We are iteratively adding noise, right?
Yes. So once you add noise, now your question will be, sir, if it is too noisy, how can I make the data? That's what I'm saying, that from a completely noisy image, you need not to make this thing. You just learn in one step. You just need to convert it into this. Now that is manageable. From this, you need to learn how can I make this. And from this, you need to learn how can I make this. With this, you need to learn how can I make this. So one time step, denoising is the thing that your network is trying to learn.
So sir, like the second part of the model is not just directly going from the 1000th noise iteration back to first. It's like going back iteratively, right? One step at a time.
Yes. Yes, yes.
It will run in an epoch manner that, okay, for 100 epochs, 1000 epochs, it will try to reconstruct the image in those epochs instead of just giving the image in the first go.
So in the backward step, it will start with this noise and iteratively try to remove small amount of noise so as to make this. Then try to remove small amount of noise to make this. And then again try to remove slight amount of noise to make this, and so on and so on and so on and so on. After capital T time step, it will try to make something which is different than this dog because of the stochasticity, and you will get a new.
Thank you. I think
Just one last thing, sir. Won't after like too many iterations, even the models it will be difficult for the model to differentiate between the noised image of a dog and noised image of a horse after we have done 1000, 1500 iterations.
So that is the point that if you do it for capital T time, and if your capital T is 10,000, then later on the initial things are not too much changing. So here it almost becomes complete image, and here it's almost like a noise. So it's okay. I mean, network has to just understand even any image. How can I remove one small amount of Gaussian noise in such a way so that it started to be aligned better to the data set that I have shown during my training. That's the loss function by which it's been trained for.
Okay, sir. Thank you.
all right. Any other questions?
Sir, I have one question.
Online participants?
Sir, actually, for creating, for using the diffusion model, ultimately we need to have a ground truth image. So, is this kind of labeling thing which we use in the unsupervised, supervised level?
Now, understood your question. Now, the point is that during training, first of all, you need an image, and then you add noise, and that noisy image has to come back to the original image. But the point is that here the labeling doesn't mean that there is a boy, that is a girl, that is a cat, that is a dog. You take any image, no label is required for that image, but just you need an image that you have added noise, so that you train your conditional neural network that okay, see, this is the noisy version, tell me the amount of noise that should I remove so that the removed noise make my image slightly closer to the original image. So you don't need the ground truth label. Yes.
Sir, one more question was from yesterday lecture. We used to design an encoder-decoder based model for a particular application. Within the encoder-decoder, we can use LSTM, GRU, or any other model. But after introduction, after this transformer concept, so will it be useful to use that kind of model? Or will the transformer concept will replace this encoder?
The transformer has already replaced this encoder-decoder model, and nobody right now uses LSTM and other stuff. So it's already being replaced, and as I have said that LSTMs are very, usually take huge amount of time to be trained for, and they are not scaled in the proper way. So that is why we have said that you can somehow try to work on transformers if you have good amount of data. Transformers are data hungry, so if you have good amount of data, you can work on that.
But sir, in one of the lectures, people mentioned that we need to have good machines or kind of.
Yes, that's what I have said that. If you have good amount of data, I am assuming that you have got high-end GPU.
So sir, is there any suggestion for a student, being a student, that online GPU, which GPU can use? If you can do that.
The online GPUs are Amazon, Azure is there, then now Colab is also having some free credits, but free credits are very less. I mean, you will have to go for Google Colab Pro. But the point is that if you wanted to train, diffusion and other things, you need bigger GPU. So now there are many cloud services. We usually do not train on cloud. But there are, I mean, Amazon, Azure and other things that you can use, KT can also help. But just use those things, bigger CPUs, otherwise you may not be able to train diffusion models or transformers.
Okay, thank you.
Yes, sir. Sir, I am audible. Yes, sir. Sir, I have one question. Sir, in denoising step, how system know that it is a noisy pixel or it is a image pixel that we want?
Can you repeat, KT sir, can you repeat because it was slightly...
The question is that how the system knows in the when we are introducing the noise in the denoising step that whether the pixel is noise pixel or is the correct pixel.
Means sir, how system knows whether it is a noisy pixel or it is a image pixel that we want.
Okay, so the point is that image, suppose that your image is of size 10 by 10, so there are 100 pixels and your noise is also of 10 by 10 size. And I take this image and take this noise and add both of them. Essentially, and the way I have said that is going to be added, I take the image and scale it by under root of 1 minus beta, and I take noise and scale it by under root of beta t, and then I add both of them. And the point is that while network, the part of my network is to predict those 100 things for each and every pixel. This guy has to tell me that what was the noise, and the amount of noise that this guy is actually telling, I figure out that what is the noise and what was the noise by which I have generated this data, and I subtract both of them, and that is the loss modeling. So network is trained in such a way so as to predict precisely for each and every pixel that how much amount of noise is essentially being added, so that if I remove that noise, the removed or the denoised version of the data becomes one step closer to the real data. So it's been trained for this. Loss function is incorporated in that.
Yes, sir. Sir, another question is apart from Gaussian noise, what are the other noises which we are added in forward pass of diffusion models?
That's a good question. So when we were discussing, I also asked my student that what are the other type of noises, and we have written to the DDPM authors as well that can we use other noises. They said that yes, you can use other noises, but essentially the under root beta and 1 minus under root beta is the mu and the Gaussian of the noise that they were actually trying to introduce. The Gaussian was having a specific mu and sigma coming from that beta term, and they said that with that beta and we have used that under root thing so as to get all of our mathematical formulation correct and very easy and simple. If you wanted to use some other parameter for your Gaussian or your Gaussian multi-model Gaussian or maybe some other type of distribution, you need to do the whole math for that, and that math becomes very tedious. So the only point is that whatever the distribution of noise that you wanted to use, it has to be a tractable distribution, well mathematically defined, and then you need to write the whole mathematical formulation. Because here, at last they have shown that the whole business of back propagation boils down to just predicting the noise. It may not be the case for, and that was because of the Gaussian noise. So it may not be the case for some other type of noise. So you need to manipulate all the mathematics. But if you ask me a simple answer to this question, you can use other type of noise, but mathematics has to be seen for all the backward and the forward process.
Yes, sir. Thank you, sir.
Any more question? Please.
Yes, sir, I have one more question. Sir.
Maybe the last
So,
question.
how does a multi-scale diffusion models bridges the gap between, for example, a microscopic scale and a macroscopic scale?
Multi-scale diffusion, so I am not much aware. Maybe some new people are talking about because I didn't have read about multi-scale diffusion. But I can say that the unit is the model which is trying to learn the noise, and you can have inception based unit, you can have some other type of models by which you can learn the error. So if it's some multi-scale network that you can use for noise prediction, that may help. But I'm not very sure. I mean, I've not seen this multi-scale diffusion model.
Yes, sir. So actually, like Indian diffusion models, they used to forget like the previous info after the forward pass, whereas the VEE models keep them as the compressed file, right? But still, our diffusion models do outperform the VAE models. So, is there any case scenario in which the extra compressed file which VAE model keeps gives them an advantage over the diffusion ones?
So the point is that diffusers are closely related to VAE, but the loss function is different. Network is to be the same. The learning is different. The VAE models are actually trying to learn the distribution, but here you can see that you are trying to learn the error. I mean, how can you learn the amount of error which is being there? I mean, the amount of noise which is being there. So learning via diffusion learning via denoising is the biggest paradigm shift from all the previous generation, basically the generation task. If you are generating something, everyone will say that okay, you need to learn the distribution. But generation problem can be posed now in two ways. One way is that you learn the distribution from which data is coming, and if you can learn that distribution, just sample from that, you will get a new data. The other way is that you can somehow learn the denoising. So if you can denoise well, you can take any noisy version data and denoise it stochastically, so that at some point of time you will get a new data, new data point. So there are two different ways. VAE's ways of learning is different by learning doing the generation, by learning the distribution, and diffusion is learning the denoising version, denoising paradigm, so as to do the generation. So both of these two things are different. Diffusion, as I have shown, that humans are also trained in a way to generate data in diffusion way. We don't learn the distribution and sample something from that. We learn how to join small dots, how to join sparser dots, and how later at some point of time you learn it in such a way so that if I give you a piece of paper, you can write the whole sentence in a single book, because you have initially been trained to join the simple dots and so forth. So you know how to denoise the steps.
Thank you, Aditya. Thank you for your patience and enlightening for this talk. And I again request all the participants to thank the speaker. And with answers to submission, is it possible for you to open your camera for a minute and just photograph? Is it possible? Aditya, can you share your camera, please?
Okay, I need to stop the presentation.
Yes, I can. We can see. Yeah.
Hello Aditya, thank you for taking the sessions. Your sessions were very wonderful, informative for the students.
Thank you very much, sir. Actually, I may not be able to deliver in the 100% because of the fact that it's not a multi-model. I was not able to use my iPad several times and also kids and everyone in the room.
But next time we will do this. Next time we will do.
Okay. Thank you.
Sir, just be Aditya, just be. Take a photo. Everybody, please see there. Thank you, Aditya. Thank you very much for your time. And maybe next time these students can join to your another workshop. And just for your information, Aditya organizes IWADL and similar kind of workshop at IIT Mandi and other various places also. You please spread this information. Just search for the IWADL, you will be getting more information. Just search for the IWADL 2020. 2019, etc. So we will conduct again the session, and you can get a chance to meet Aditya. Aditya, thank you very much. It was a wonderful session, and really this is a very complex topic, and you have simplified us for our audience, and hope this can take it forward and learn at their pace. Thank you. Thanks.
So 25 we will do here only, if possible.
Yeah.
Okay. Thank you, sir.